So, in the last class we discussed Nyquist stability criteria. So, today we will continue that topic with an example. So, today we will continue the Nyquist stability criteria. With an example. Now, the closed loop transfer function is given as 0.8 Kc divided by 5s plus 1 multiplied by 10s plus 1 multiplied by 15s plus 1. The open loop transfer function is given in this form. Open loop transfer function. Here Kc is the proportional gain, controller gain. Now, we will perform the stability analysis by developing the polar plot with varying omega from minus infinity to infinity. Next, we will perform the stability analysis by developing the polar plot with varying omega from minus infinity to infinity. So, in first step we will replace S by j omega. In the first step we will replace S by j omega. Accordingly, we get the frequency response transfer function as ZOL equals 0.8 Kc divided by 5 j omega plus 1 multiplied by 10 j omega plus 1 multiplied by 15 j omega plus 1. This is the frequency response transfer function. Now, we can write the expression for amplitude ratio and phase angle phi. So, we can say that this is the three first order systems are connected in series. This indicates that the three first order systems connected in series. So, it is straightforward to write the expression for amplitude ratio, that is 0.8 Kc divided by 1 plus 5 omega square multiplied by 1 plus 10 omega square multiplied by 1 plus 15 omega square. This is the expression for amplitude ratio. Similarly, we can write the expression for phase angle phi, that is tan inverse minus 5 omega plus tan inverse minus 10 omega plus tan inverse minus 15 omega. These are the two expressions, one is for amplitude ratio and another is for phi. Next, we will go to the second step. step 2. In this step we will vary omega from 0 to infinity. I have mentioned that we will develop the polar plot by varying omega from minus infinity to infinity. So, that range we will divide into two ranges, one is from minus infinity to 0, another one is from 0 to infinity. So, in step 2 we will vary omega from 0 to infinity. To infinity. Under this we can say that the polar plot starts at omega equal to 0. Polar plot starts at omega equals 0. Now, at omega equals 0, what is the corresponding amplitude ratio that we can get from that expression which we have written? When omega equals 0, amplitude ratio becomes 0.8 kc. Similarly, if we can determine the value for phase angle. How much is the phase angle when omega equals 0? 0. So, when omega equals 0, we can obtain amplitude ratio 0.8 kc and phi 0 degree. Now, polar plot terminates at omega equals infinity. When omega approaches infinity, the polar plot ends. So, when omega equals infinity, we obtain the corresponding amplitude ratio as 0. Similarly, if we obtain phi minus 270 degree. Fine. When omega approaches infinity, we obtain amplitude ratio 0 and phi minus 270. So, when amplitude ratio is 0.8 kc and phi 0, the starting point will be on real axis. You see phi is 0. So, the starting point will be on real axis. Similarly, when amplitude ratio is 0 and phi minus 270, the end point will be on in origin. This indicates the origin. Agree? Now, we will draw the polar plot varying omega from 0 to infinity. So, this is a complex plane, real axis, imaginary axis. This is a unit circle. This is unit circle. Fine. That means this point indicates 1 0 and this point indicates minus 1 0 and this is the origin. Fine. Now, the plot starts at omega equal to 0 when amplitude ratio is 0.8 kc. So, we will consider kc value unity 1. That means, this will be 0.8, amplitude ratio will be 0.8 if kc is 1 and phi is 0. So, we can locate the point say here. This is the point, starting point. So, this starting point we obtain when omega equal to 0. This is the starting point which indicates amplitude ratio is 0.8 and phi is 0. What about the end point? At end point amplitude ratio is 0 and phi is minus 270, that means this. So, if we join, then we obtain the plot like this. Fine. So, this is the polar plot and direction is this. This is the direction of this plot. Definitely we obtain this polar plot considering Kc equal to 1. This is the starting point at omega equals 0. This is the end point origin when omega equals infinity, and this is the polar plot when Kc equals 1. So, this is polar plot with varying omega from 0 to infinity. In the next step, I mean in step 3, we will vary omega from minus infinity to 0. In the third step, we will vary omega from minus infinity to 0. So, vary omega from minus infinity to 0. Now, plot starts at omega equal to minus infinity. Polar plot starts at omega equal to minus infinity. What will be the corresponding amplitude ratio? Corresponding amplitude ratio is 0. What about phi? Phi is 270 degree. So, at omega equal to minus infinity, we obtain amplitude ratio as 0 and phase angle phi as plus 270 degree. So, what about the point location of the point, starting point? Origin. So, the location of the starting point is origin. Similarly, if the plot terminates at omega equal to 0. What about the corresponding amplitude ratio? Amplitude ratio is 0.8 Kc. What about phi? 0 degree. So, when omega equal to 0, we obtain amplitude ratio as 0.8 Kc and phi 0 degree. So, what about the location? On the real axis. Fine. The location of the end point should be on real axis. Now, we will draw the polar plot for this case. I mean from varying omega from minus infinity to 0. This is real axis in complex plane, this is imaginary axis. Similarly, we need to draw the unit circle. This is the unit circle. So, this is 1 0 and this point is minus 1 0 and this is the origin. So, plot starts at origin and amplitude ratio is 0 and phi is minus 270 and plot ends when amplitude ratio is 0.8 kc and phi 0. So, for this case, in this case also we will consider kc 1. So, this is the starting point and this is the end point. Starting point we obtain considering omega minus infinity, end point we obtain considering omega 0. So, the polar plot is obtained as this. This is the direction clockwise. So, this plot we obtain when kc equal to 1. This is suppose figure 2. Polar plot with varying omega from minus infinity to 0. This is figure 2, which is basically the polar plot with varying omega from minus infinity to infinity, and previously we obtained polar plot with varying omega from 0 to infinity. Suppose this is figure 1. In figure 1 we obtain polar plot with varying omega from 0 to infinity, and in figure 2 we obtain polar plot with varying omega from minus infinity to 0. Now, you see figure 2 is the mirror image of figure 1. It can be observed that this figure 2 is the mirror image of figure 1 with respect to the real axis. So, figure 2 is the mirror image of figure 1 with respect to the real axis. Fine. Previously it was mentioned that we will produce the polar plot by varying omega from minus infinity to infinity, but we have drawn two plots. In one case we have varied from 0 to infinity, and in another case we varied from minus infinity to 0. Now, we will combine these two plots. So, in the next step we will perform the stability analysis. In the next we will perform the stability analysis, and for that we will combine the two figures, I mean figure 1 and figure 2, so that we can show the polar plot with varying omega from minus infinity to infinity. So, this is the complex plane This is real axis, this is imaginary axis. This is the unit circle. This is the unit circle. This point indicates 1 0 and this point indicates minus 1 0. Fine. So, we will consider Kc equal to 1. Then when we varied omega from 0 to infinity, then we obtain this plot. You can say this is figure 1. Similarly, as we varied omega from minus infinity to 0, we obtain this plot. Agree? So, this plot we obtained by varying omega from 0 to infinity, and this plot we obtain by varying omega from minus infinity to 0, and this polar plot corresponds to Kc equal to 1. Now, this point is called cross point. The point C is called the cross point. C is called the cross point. Fine. Now, we will note down few important points on stability. You see, when Kc equal to 1, the cross point is to the right of minus 1. When Kc equal to 1, the cross point is to the right of minus 1. It indicates stability. When the cross point is to the left of minus 1, that indicates instability. I mean, the system is unstable. Fine. So, when Kc equal to 1, the cross point C is to the right of minus 1. That means the system is stable. We can define it in another way. You see, the plot corresponding to Kc equal to 1 does not encircle minus 1 0. Therefore, the system with Kc equal to 1 is stable. The polar plot corresponding to Kc equal to 1 does not encircle minus 1 0. That means the system is stable. If we consider Kc equal to 2, what happens? If we consider Kc equal to 2, suppose this is the unit circle, in complex plane. If we consider Kc equal to 2, then this becomes 0.8, I mean 0.8 multiplied by 2 is 1.6. So it will be like this. The polar plot will be, suppose this is indicating 1.6. So this is the polar plot by varying omega from 0 to infinity, and this is the polar plot by varying omega from minus infinity to 0. This is the polar plot when omega varies from 0 to infinity, and this is the polar plot when we vary omega from minus infinity to 0. Which one is the cross point? This one, and this is the minus 1 0 point. Fine. You see, when Kc equal to 0, the cross point C is to the left of minus 1. So, when Kc equal to 2, the cross point C is to the left of minus 1. So, we can say that the system is unstable. Fine. So, by this way we can apply the Nyquist plot for stability analysis, and this criteria can be used for tuning the controllers. So, this is all about Nyquist plot. Next we will discuss another tuning method, that is Zn method, Ziegler Nichols technique. In the next we will discuss another tuning technique, that is Zn tuning method. Ziegler Nichols tuning method. This was proposed by Ziegler and Nichols in 1942. This technique was proposed by Ziegler and Nichols in 1942. This technique is also based on frequency response analysis. This technique is also based on frequency response analysis. Fine. And this technique is known as closed loop tuning method. This technique is known as closed loop tuning method. This technique can also be used online. I mean, when the process is in operation, we can use this technique for tuning purpose. Therefore, this technique is also sometimes called online tuning method. So, this technique is called closed loop as well as online tuning method. Fine. So, in the next we will discuss how we can use this technique for tuning purpose. We will know the several sequential steps for applying this technique for tuning purpose. So, we will discuss the step wise procedure. At first you bring this process to the steady state condition. In first step we need to bring the system to steady state condition. So, bring the system to the steady state condition. This is the first step. Secondly, use the P only controller. You cannot use PI and PI or PID. So, first you use P only controller. At the same time you close the loop. So, close the feedback loop. Fine. Apply the P only controller and close the feedback loop. Then introduce a set point change. Then introduce a set point change. Fine. So, first we need to employ P only controller, not PI or PID. At the same time you close the feedback loop. Then introduce a set point change. Then we can tune the controller. I mean, we will vary the Kc value so that we can obtain sustained oscillation. So, next keep on varying Kc value. So, I am writing vary Kc value which is proportional gain until the system oscillates with constant amplitude. Fine. So, under this second step use P only controller, at the same time close the feedback loop, then introduce a set point change, then vary Kc values so that we can obtain sustained oscillation. This is step 2 in the procedure. Next, determine ultimate gain. Determine ultimate gain. You see the last point under second step, we have in the last point of the under second step we have mentioned that vary Kc value so that we can obtain sustained oscillation. That Kc value is basically ultimate gain. Fine. So, ultimate gain means the process gain that provides the condition of amplitude ratio equal to 1 at phi equal to minus 180 degree. Ultimate gain is the controller gain that provides the condition of amplitude ratio equal to 1 at phi equal to minus 180 degree. We can say that the value of Kc at which we obtain sustained oscillation, and this is represented by K suffix u. Ku is the value of Kc at which we obtain sustained oscillation, and this corresponds to the condition of amplitude ratio equal to 1 at phi equal to minus 180 degree. In the next step, we need to determine the ultimate period. In fourth step, we need to determine ultimate period of sustained cycling. Fine, and this ultimate period will represent by P suffix u. What is ultimate period? Ultimate period is time between two successive peaks in continuously oscillating process output. Ultimate period is the time between two successive peaks in the continuously oscillating process output. Continuously oscillating process output. It is somewhat like this. Suppose this is y, this is t. It is continuously oscillating like this. So, this is the ultimate period Pu. Fine. You see, this is a continuous oscillation. So, the time between two successive peaks, that is Pu. Now, we can determine it also mathematically. What is period of oscillation, which we represented earlier by T? Period of oscillation T equal to 1 by f. F is the cyclical frequency. This is equal to 2 pi by omega. Basically, omega is 2 pi f. Fine. The period of oscillation T is 1 by f. F is cyclical frequency. This is equal to 2 pi by omega. Now, if we consider sustained oscillation, that means what? Omega equal to omega C O, crossover frequency. Therefore, we can write this Pu equal to 2 pi divided by omega Co. Fine. So, this is the ultimate period of sustained cycling. So, in step 3 we knew the calculation of ultimate gain, and in the next step we discussed the determination of ultimate period. Now, knowing the values of Ku and Pu, we need to use some correlations recommended by Ziegler and Nichols. Fine. So, we will know the different correlations which have been proposed by Ziegler and Nichols. Controller type, proportional gain Kc, time constant tau I in minute, derivative time tau d in minute. For P only controller, Ziegler and Nichols proposed the expression for Kc, which is equal to Ku divided by 2. Fine. For Pi controller, the correlation is Ku divided by 2.2 for Kc, Pu divided by 1.2 for tau I. Next is PID controller. For PID controller, Kc is Ku divided by 1.7, tau I is Pu divided by 2, and tau d is Pu divided by 8. You see, all the correlations depend on only Ku and Pu. So, knowing the values of ultimate gain Ku and ultimate period Pu, we can use these correlations recommended by Ziegler and Nichols for finding the control parameter values. Fine. Now, important points we need to note down now. First point is the tuning relations are determined empirically to provide 1/4 decay ratio response. These correlations are determined to provide 1/4 decay ratio response. Fine. This is the first point. These correlations have been determined to provide 1/4 decay ratio response. I mean, the decay ratio should be 1/4. Secondly, for P only controller, the safety margin is 2. For P only controller, the safety margin is 2, because Kc is equal to half of the stability limit. You see here, Kc is equal to half of the stability limit, that is Ku divided by 2. Therefore, the safety margin for P only controller is 2. Next, if you see the correlations, we observe that the proportional gain for P only controller is greater than the proportional gain of Pi controller. if you see the correlations, we observe that the Kc of P only controller is higher than Kc of Pi. What is the reason? Because integral mode introduces additional phase lag with destabilizing effects on the system. Because integral mode introduces additional phase lag. Integral mode introduces additional phase lag with destabilizing effect on the system. Another important point is under this, lower Kc maintains approximately the same safety margin. Lower Kc maintains approximately the same safety margin. Lower Kc maintains approximately the same safety margin. Fine. In the last point, we will discuss, we will compare the Kc value of all three controllers. You see the Kc value of PID controller is greater than Kc of P only, and that is again greater than Kc of Pi. Fine. So, the Kc value of PID controller is the largest one, because the derivative action introduces phase lead with stabilizing effect on the system. For PID controller, we consider large Kc value because derivative action introduces additional phase lead. You write phase lead, derivative action introduces phase lead with stabilizing effects on the system. Fine. So, these are the steps related to the Ziegler Nichols technique. Next, we will solve one problem in which we will apply this Ziegler Nichols techniques for finding the tuning parameter values. Example, open loop transfer function is given as Kc exponential of minus 0.15 s divided by 0.5 s plus 1. Open loop transfer function is given as Kc exponential of minus 0.15 s divided by 0.5 s plus 1. Fine. Here time constant is 0.5 and date time is 0.15. Now, tune the PID controller using Zn technique. Tune the PID controller using Zn method. Fine. So, first you determine crossover frequency. Determine crossover frequency. See, in this open loop transfer function we have considered only P controller. Fine. In this open loop transfer function we considered only P controller. So, this is basically GC, GP, GF, GM, no. Here we have considered GC equal to Kc. Fine. First you determine crossover frequency. For determining crossover frequency, we write phi equal to minus 180 degree. What is the phi expression for the open loop transfer function given? Tan inverse minus 0.5 omega CO, 0.15 omega CO multiplied by 180 divided by pi, that is equal to minus 180. If you solve, you will obtain crossover frequency as 11.6 radian per minute. This is the value for crossover frequency. Then determine ultimate gain. Determine ultimate gain. We can obtain ultimate gain if we consider amplitude ratio equal to 1 at crossover frequency. Fine. Ku is the value of Kc at which we obtain sustained oscillation, and that corresponds to the condition of amplitude ratio equal to 1 at crossover frequency. So, what is the expression for amplitude ratio? Kc divided by 0.5 multiplied by 11.6 whole square plus 1 equal to 1. Fine. This is the expression of amplitude ratio and that is equal to 1. So, if we solve it, we obtain Kc value 5.89 and this is nothing but ultimate period, sorry, ultimate gain Ku. Next, determine ultimate period. What is the expression for Pu? Pu is 2 pi divided by omega Co, that is equal to 0.542 minute per cycle. So, ultimate period is, ultimate gain is 5.89, ultimate period is 0.542. Now, we can easily use the correlations to determine the 3 tuning parameter values for PID. So, for PID controller, Kc is Ku divided by 1.7. Using the value of Ku, we obtain 3.465. This is Kc. Integral time constant has the form Pu divided by 2. Using the value of Pu, we obtain 0.271. Now, derivative time is Pu divided by 8 and this is equal to 0.068. So, by this way we can tune P only and PI controller also. Fine. So, today we discussed the Nyquist stability criteria with an example. Then we discussed the theory involved in Ziegler Nichols technique. Then we discussed one example to apply that ZN technique. Thank you.